Well, welcome back, everybody. I think our first day at Icons 2020 was extremely successful. I think the presentations we had were outstanding. The keynotes were great. We didn't have any major technical glitches, which was especially good. So anyway, thank you all for taking the time to attend. I thought it was a very productive session. This year we've got a very special keynote speaker. This arose from a meeting we had last year. So last year in Knoxville, we had a reception in a bowling alley. Now I know that doesn't sound very glamorous, but this reception is actually in this very fancy bowling alley. We call it a hipster bowling alley, so it's very fancy. And so we were in the bowling alley, and a gentleman, Matsumi Kimura, comes in and he says, I've just arrived from Japan. It took him about 2 days to get there with travel delays. And he said, I'd like to talk to you about hosting this meeting in Japan. And he had this beautiful presentation laid out, well thought through. So we had this wonderful discussion. And with all the COVID changes and shifts and all that stuff, we're looking to do that in 2 years. But Matsumi very graciously said, well, let me see if I can get some of the top scholars from Japan in neuromorphic computing to come and give a keynote. So Matsumi, would you mind introducing the keynote speaker this morning?
Okay, thank you. Good evening from Asia. Okay. And I'm Mutsumi Kimura from Ryukoku University, and simultaneously I belong to the Nara Institute of Science and Technology, Japan. Okay, it's my pleasure to introduce Professor Akira Hirose, the University of Tokyo. The detailed information of Professor Hirose is written in the website of the icons. But briefly, I would like to introduce that for example, he's a very famous person in the area of the neural network. And for example, he's the founder of Asia Pacific Neural Network Society. And he was vice president for IEICE. This is the biggest conference in Japan about the electronics. And he's also a fellow of the IEEE and IEICE. And what I would like to say the most is that he is one of the authority on the reservoir computing. Okay, so shall we enjoy his keynote address? Professor Hirose, are you ready?
Yes, thank you very much, Professor Kimura. Thank you very much. Good morning, good afternoon, and good evening. Today, I would like to talk about physical reservoir computing devices and complex valued neural network. Well, I'm actually working in not only devices, but also measurement, imaging, and so on, which use neural networks. But today, I would like to concentrate upon the neural devices or neuromorphic devices, focusing on the reservoir computing, in particular, spin wave reservoir computing. This is the outline. AI, artificial intelligence, hardware history, and then essence of neural networks, and reservoir computing, spin wave reservoir computing chip. And in addition to this chip, I explain a little bit of complex valued neural networks. The first, AI hardware. I think this is something like preaching to the choir. All of you are professional in this field. But anyway, I do a very brief summary. The AI hardware has a very long history, actually. In the case of Japan, in 1980s, the NEC Corporation, for example, sold the Neuro board. It is an additional board to be included in a personal computer. This is a magazine written in Japanese. And on the back cover, we can find the advertisement of the product of NEC Corporation, personal neuro computer board using an IMPP, that is image pipeline processor, MUPD7281, developed in 1984. Well, it says, it is in Japanese, sorry, but it can realize back propagation, 5 layers, 216 kilo links per second speed, 110 kilowatt memory, kilowatt, not mega, not giga, but kilo, and so on. Well, this is the photo of the board, and but the architecture is very attractive. This is the IMPP linked circularly in this case, and it is based on the data flow pipeline processing framework. And but in 1990s, many people are attracted, and now also in the analog type neural devices. For example, this is a floating gate transistor working as a neuron, proposed by Shibata Sensei's group. They had a floating gate here, and the input gates are located here, and it works as the weighting and summing operation. And they expected to make a large-scale analog neural network by using this type of devices. Carver Mead, of course, worked also in this field by injecting electron to the insulator. The memory was also included then, and the neurons were placed two-dimensionally, systematically, and large-scale neural networks were expected to be realized. Periphery, such as input-output I/O circuits are also investigated very actively. Mead also developed the resistive networks, silicon retina, which realizes the differentiation of the input signals in the space domain. This is based on the retina of the human beings and other animals. It realizes this very big dynamic range. Neuro vision chip was also developed. This is the name of this device, developed by the Mitsubishi Electric Corporation. In the CCD, the charge-coupled device, we normally read the charges sequentially, but in this process, they proposed to do very simple but effective arithmetic calculation that realizes, for example, addition or subtraction of the data neighboring to each other. So this is the output. This is a normal or output image, but when they change the reading mode, they can realize the edge detection. And this chip is now widely used in the computer game hardware and sometimes in the smartphones. Well, in 2000, memory stars, the big topic in the field. It was proposed originally in 1971 by Chua, and at that time he presented an analog circuit of this kind to realize the hysteresis in the resistors or capacitor or inductors. And because of the memory function, people expected that this kind of devices will lead to neurons with weight memorized on the device locally. And now that kind of device is evolving into nano or micro scale physical devices of this kind, phase transition device and other devices. They are analog in this sense. But afterwards, one epoch was true north. It works based on the spiking neurons and also digital processing. True north chip is explained here. This is a layered neural network having an input layer that is arrayed terminal, and they are the neurons, and it makes output adaptively. This is the biological inspiration, but this is the realization in the electronics. This is the input terminal, and they are the neurons. And in between, they located the crossbar type switches or waiting points. Dendrites and axons. Well, probably axon should be here, but it can be axon because it is after the connection or waiting. So this is the core of the neurosynaptic processor, true north. And the point of this device or the use of the spiking neurons is the ease in weighting operation or product operation. That is, by generating pulses randomly, hopefully, then one time sequential pulses can be used as the weight to be multiplied to a signal, which is also represented by the pulses, pulse train. By preparing gate, simple AND gate, and we feed the weight pulse train and the signal train, we can realize the weighting operation in terms of the pulse frequency or pulse density in the time domain. Normally, the multiplication requires a lot of gates and resulting in the power consumption. But this type of multiplication is very simple. So this is very attractive. Local spike operation, so not so high power consumption, and remote parallel bus transmission, which is used between the core and another core to realize stable communication. So it worked very, very well, and still attracts many people. And in these years, many people use GPUs in the neural network field. Probably you also use GPUs or TPUs. Well, this is very digital and based on data flow, systolic pipeline architecture. TPU, Tensor Processing Unit, developed by Google. So they basically developed the matrix multiply unit and very high speed data bus based on the historic digital processing. It is very, very useful, and many people use it. So that pipeline of 40 years ago was might be very primitive, but the basic structure or framework is not so old. Pipeline, systolic, data flow, and resistiveness is also very important. So digital, well, GPU, TPU, and spiking neural networks very special, but it worked very well. And in the analog resistiveness, the memory star device, they are devices. They work very well. They will work very well, probably, in the near future. But history is always going this way. Well, sometimes we go to digital very, very much. Sometimes analog, sometimes digital again, and analog also, and so we swing to this side, and then this side. We come back this side, but the level is higher than it was. This is the development direction or development process. And I would like to put the physical reservoir here. Well, it is just started, but I believe that this type of hardware has a very wide and important role in the neural network processing. Well, at present, including TPU, GPU, and so on, I think there are two big problems in the hardware. One is the element variability. Because of the reduction of the size of the elements, so transistors, the number of the atoms reduce and reduce and reduce, and then the standard deviation of the characteristics becomes very, very much large in comparison with the average. So in the normal logic, we have much error, much more error in the near future. And another one is the wiring explosion, in particular in neural networks. The transistor can be smaller, 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 but the wiring is not so getting smaller, relatively. And well, this is one of the very serious origin of the power consumption. Well, we charge up the wire, which discharge the wire, charge up, discharge, and so on. Then it leads to a very big power consumption. And I think the pattern information representation and the pattern information processing in the hardware level will solve these problems. These 2 points are the essence of neural networks. What is the essence of neural networks? This is a PC on my desk. We can see the Intel and memories and video cards and so on. In comparison with this PC, this is a brain captured by MRI. And actually, this is my brain. When I had a very serious headache, I asked the doctor, please take the MRI image. And it is very, I was relieved to see something is inside. And the doctor said, no, okay, no problem. You are not a patient. I'm also relieved. And I asked the doctor, I would like to make a copy of this data so that I can make use of this image in my presentation or in my classes. and here it is. So we have eyeballs here, and a part of brain seen here. In this sense, the I/O is clearly separate, or of course connected, but separate by the brain. This is a cut a little higher than the eyeballs, this level. And then we can see the brain part. Anyway, we have the brain. I have the brain. This is a little more higher. Then we can see clearly the folding pattern. Oh, great. But we cannot say this is the Intel CPU. This is the memory. Very different. And in the close-up, we can see the neurons. This is not my neuron, but just well, one cat. And this is a pyramidal cell, as you know. And we have it has many dendrites, and we have an axon here, but with this scale, we cannot see clearly. It is very thin. And when we look it a little far, then we can see the layer of the soma here. And the dendrites run very almost at random, making connections. Why it works? This is the problem. The dendrites make connections, but they are almost at random. Sometimes the soma locations are also very at random in another part. Why it works? Well, in the Intel case, the engineers, many engineers work on generating, creating the chip by designing the circuit, the locations, and so on. And they do the debugging, and many months later, they sell the elaborated Intel chip. But our brain is almost at random, but it works. Why? So Makarov-Pitts model is the most basic model of a neuron. Probably you are also familiar with this type of model. In this case, they paid attention only to the pulse rate in time. So average pulse number represents the information. And nonlinearity is also included. And then this is the mathematical expression showing the function of a neuron. So xi is the input, wi the weight, and we may have a threshold, and weighted sum minus threshold and the saturating function generates the output y. Okay. But this is actually very similar to a gate. This is the conventional logic gate, and we have 3 inputs here, and the mathematics representing this gate is here. We sum up the input, and we probably set the threshold at 2.5. And 1, this is a function, step function shown here. And this is the output. Well, even only if all the inputs are 1, 1, 1, then minus 2.5 is positive, and we get 1. And if we have 0 or zeros, then it is 0. The equation is very similar to that of the neurons. Then what is the difference? Well, we interpret the difference in the following way. This is the neurons, this is the gates. They are very similar, but in the neuron case, a neuron has many, many inputs. Many, many inputs. And well, continuous weight may work well, but it is less important, actually. This many inputs realizes the pattern information representation and pattern information processing. Here, the pattern means not the image or real pattern. Instead, it is a very abstractive pattern. That is, information is represented in the cooperation of many neurons that make connections to this neuron. Here we have neuron, many neurons, and together they represent information. This is very different from the von Neumann type representation, that is symbol information representation. Symbol means flag or bit. One bit is very important. If one bit changes, then the result is very, very different. This is because the number of the input is very small. Well, neural networks are based on the pattern information representation. It means the use of inner product or correlation, inner product, or the correlation between the weight and the signal, input signal. And the result also works as the output. In this sense, the pattern information also realize the processing itself. So inner product generates the output. But in the von Neumann type or logic type computers, the symbol is very important. Bit is very important. And well, so yes, actually, every day we lose neurons, 10 neurons or 100 neurons every day. They are cells, and cells die. But we can live a day. If the PC loses the transistor, 10 transistors a day, then the PC doesn't work. Because one bit is very important in PC. And this point is directly related to the generalization ability. This is the most important function we expect in the neural network. We take an example of supervised learning in the neural network. We consider this is the input X, and this is the output Y. and they are the teacher signals. For input 2, we expect output 5, input 4, output 6, input 7, output 4. So by applying the supervised learning algorithm, we expect that the neural network learns these points. The error goes to 0. But actually, what we expect is to obtain this curve, not zeros at these 3 teacher points. Instead, we expect this curve. This is the estimation or prediction. They are the most important function in neural networks. If it is not, well, if we don't expect any estimation or prediction, then we will make a very simple lookup table in the logic circuit. For the input 2, we expect 5, 4, 6, input 7, output 4, and we may have many inputs and many outputs. It's okay. We will make the truth table, and we will realize the circuit. Every undergraduate learns how to make truth table and how to design the circuit. The neural network is a little different. If it has a new example teacher signal, then the curve will be changed here. But at the same time, the curve at another or other areas can also change. This is the imagination ability or the generalization. So some machine may work as listen billions, then it understands millions. Many teachers, and it works well, but the working environment will be almost the same in its number. We don't expect this one. Instead, listen thousands and understand billions. Small teachers, but it works very well. We expected this function. This word was also used by Fukushima sensei, Kunihiko Fukushima professor, who is the father of the convolutional neural network. He developed the convolutional neural network in 1979. Now it is widely used more and more, as you know. Well, I was chairing his keynote session last week. Kathy knows. Well, that is the essence of the neural networks. Then, what happens in hardware? Well, this is the principle of neural AI. Now, the AI is not logic, but the neural AI, based on the pattern information representation and processing. But the hardware is based on the bit machine. Present numerical calculator, PC, supercomputers, they are working as a von Neumann type or a logic machine. And the first one is ENIAC and other same year development about 70 or more years ago. But there is a discrepancy between this hardware basis and the principle of the AI mathematics. If we can realize neural AI devices based on the pattern information representation and pattern information processing that is inner product and correlation, then we can realize a very different world. And this is consistent with the present neural AI. And probably in the future, we will use both of them, neural AI devices, machines, and also the bit machines in a complementary way. So, well, this is a history. Here on the left-hand side, we have the brain information investigation techniques. The people developed many ways. And in parallel, symbol information representation processing hardware was developed very actively and continuously. And logic AI was once developed very successfully, but now we realize that the neural AI is indispensable for the future development. And in the neural network, we had many epochs. Neocognitron is the first one of the convolutional neural network. And sound clock neural networks are also very important in the present many layers of deep learning neural networks without convolution. Developed by, say, Cottrell, Professor Cottrell, and other several groups. And now we use them in the AI processing as an algorithm, but we don't have developed the neurotype pattern information represented and processing type hardware, not yet. This is the problem. Then, the time is running. Reservoir computing, sorry. Well, reservoir is water reservoir, pond or something. But in this context, it includes many hidden neurons with recurrent and random connections. And they are the input terminals, and they are the output neurons. And we apply the learning process only to this output connections. If we also apply the learning process in the reservoir or this recurrent part, we call it recurrent neural network. It works, and we have several algorithms working very well. But it takes a long time normally and consume a lot of electric power. And the reservoir computing people found that if we have many neurons, it works very well, even if it doesn't go through a learning process. Without learning process, it works. And theoretically, it was proposed in early 2000. And we also made a review paper very recently by focusing on the physical reservoir hardware. We can realize it is very important, also important that the reservoir can be realized by physical phenomena or physical phenomena. Well, some people use optics. Sorry. Sometimes, well, we use spin waves. And if it is realized physically, then it means that the pattern information representation and the pattern information processing is also realized physically. And in many cases, physical reservoir implements a huge number of neurons. So this type of devices are consistent with neural essentials. So high generalization, time sequential processing. So our brain is basically working in time sequence, not snapshot in time domain. And the device is non-elaborated. It means, I don't know how to say, but well, Intel case, engineers work very, very hard and make it right. But in the brain case, the rough, we may have the rough design, well, diagram in the DNA, but it is basically randomly connected, and in the when it is exposed to the environment, it learns how to work. Physical reservoirs, some physical reservoirs are shown here. Probably the first one is this one, figure one, the liquid brain, or the calculation in a bucket. It contains water here in the bucket, and it is well, the wave is generated at these points mechanically, and by observing the wave by using the overhead projector. Young people don't know overhead projector, but it is an optical imaging system, very simple. By observing the wave, the camera can get the information two-dimensionally, and we can realize information processing. This one is soft matter information processing. Just like it seems like octopus legs, foot. But anyway, it has sensors on the surface, and by fluctuating the root of this soft matter, it makes a very complicated movement, and the sensor catches the output of a type of transformation of the input signal. They are very, very interesting. But finally, we like to make that kind of function in optics or electronics. Well, optical reservoir is proposed in many ways. This is a type of laser diode and external cavity feedback nonlinear system. And this is a spin torque system. Please refer to these papers. And the application fields are very, very wide. In particular, in the edge computing of the sensor network system in the society. At the end of or the edge of the network, it works very well. In that case, we expect ultra low energy consumption because the number of the edge computers are very, very huge. That's why. Okay, 5 minutes or 10 minutes. Spin wave reservoir computing chip. This is our proposal. We use garnet film and some electrodes, input electrodes in red, output electrodes or readout electrodes in the gray. And we generate a spin wave in the garnet film, and we pick up the wave information. Well, as you know, the spin is something like this one with the precessional motion, and they are connected loosely with each other. Then the precessional motion propagates to the neighboring spin, neighbor. And then we observe a wave. And the external magnetic field is very strong. It is very firmly fixed, and the precession motion is very small. But when the external field is getting lower in its magnitude, then the motion goes this way very loosely and with a large fluctuation, and it realizes not only the propagation or delay, but also the nonlinearity, hysteresis, dispersion, and so on. Then the input signal is transformed into a higher dimensional information, time sequential information, with this rich dynamics. And we realize sometimes the edge of chaos, which is very useful, it is said, in the reservoir computing. And we did so in this case, the simulation experiment, physical or numerical experiment, spin X direction component, Y direction component V, and we observe the waves reacting to the input, propagating outward. And it is history sensitive, or it has a hysteresis. And by using this, and also nonlinear propagation. And by observing the output of the readout electrode at the readout electrode, we can realize the type of generalization. Well, sorry, I skipped these pages, but it realizes the most important point of neural networks to generate non-learned output. And the complex values neural networks are also very important. I will use some pages. Well, many people were working, of course. But, okay, I use this page. Complex valued neural networks. What is its generalization ability? Again, but in the complex domain. Well, we consider a very simple neural network, 2 inputs, 2 outputs. This is input X in 2 dimensions, and this is the output. And we apply the learning process to determine the optimal W11, W12, and so on. And we may have a nonlinearity here and to get output. And we often observe this type of learning result. Well, this is non-degenerate, well, degenerate result. So the dimension is, has shrinked. In many cases, this type of transformation is not so useful. This happens because of the too large freedom. Reduction of the freedom often leads to better performance in the learning or self-organization. It is a type of sparsity. Well, we consider this situation as the neural network in complex domain. Then what happens? We have 1 input, 1 output, but they are complex numbers. And then, as the learning result, we get this transformation because we have only 2 variables or parameters instead of 4 parameters. And this matrix, this is a complex number, but in an abnormal representation way. Well, this complex number means the rotation of angle theta and scaling of W absolute value. And that's all. Of course, we may have 2n pi arbitrarity, but it's okay. It's not so important. In this way, we can determine the transformation uniquely. And this situation is very simple, but when we have many neurons, then it works very effectively. And we can get very useful generalization ability, useful to represent wave phenomenon. And well, this amplitude corresponds directly to the energy, and phase corresponds directly to the time or space difference. In this sense, it is also very important. And well,
Professor, because of the time limitation, could you hurry up?
Yeah, thank you. In this way, because the spin wave chip works with the wave, so it is very important. And actually, optical reservoir also works with wave. So the wave-based hardware, probably based on the complex valued neural network framework, will be more and more important. So we are going to realize that kind of chip, and it will be the ENIAC of 70 years ago, but the modern new start of the AI, neuro AI hardware. Thank you very much. Sorry to be late. Thank you very much.
Thank you very much for very interesting talk. It's time to ask a question, but very sorry that we would like to accept a very short question. Do you have some question?
Well, I have a quick question. Thank you very much for your talk. It was that was very, very interesting, and I really appreciate that. With when I was looking at some of the complex domain, it sort of was reminiscent of some of the work I've seen done in the quantum space. Have you thought about maybe a bridge between some of the complex domain and quantum computing?
Yeah. Yes, quantum computing is one of the very important field. Some people apply this framework to the quantum computing.
Thank you.
Okay. So because of a limitation of the time, we are sorry, but we have to end his presentation. Let's thank him, the presenter, Professor Hirose, again. Thank you very much. Let's
Thank you very
clap
much.
your hands.
Thank you.